You've been there, right? You've got 5 bars of Wi-Fi in the living room, you take literally 2 steps into the kitchen and gone. Nothing. It feels so random, but I promise you, it's not. It's all about physics, and it's actually pretty fascinating. So let's follow that signal and uncover the invisible journey it's taking through your home, right now.
Because that signal's journey is almost never a simple straight line. It has to overcome all sorts of things just to get from your router to your phone.
You know, to really get what goes wrong in our world, we first have to imagine a perfect one. So picture your Wi-Fi router, but instead of being in your living room, it's just floating in the total emptiness of outer space.
Okay, so in this perfect empty space, a signal only has one enemy: distance. We call this free space path loss. The best way to think about it is like ripples in a pond. The farther they get from where the rock dropped, the smaller and weaker they become. It's just a fundamental, predictable rule of physics.
Now, this simple rule has a really powerful consequence. See that little squared symbol at the end of distance? That's a huge deal. It means if you double your distance from the router, you don't get half the signal power. No, you get only 1/4. The signal strength drops off incredibly fast, and that's even in a perfect world with nothing in the way.
But of course, none of us live in a perfect vacuum. Our homes, our offices, our cities, they're all just a crazy, complicated obstacle course for that signal. And this is where that nice, simple journey gets really, really messy.
So 3 big things happen to your signal as it tries to navigate this course. First, you've got reflection. That one's easy. The signal just bounces off big, smooth things like your walls. Then there's diffraction. That's how a signal can actually bend around a corner, which is kind of cool, and it's why you can get a connection even when you can't see the router. And finally, there's scattering. That's when the signal hits something rough, like a brick wall or even a plant, and it shatters into a ton of weaker copies of itself, going everywhere.
Okay, so given this wild obstacle course, how do we give our signal a fighting chance? Well, the answer is antennas. And here's the key thing. Antennas don't create more power. What they do is focus the power you already have right where you need it to go.
The best analogy is light. A theoretical antenna, what we call isotropic, is like a bare light bulb. It just sends light, or in our case, a signal, out equally in every single direction. It's a useful idea for calculations, but it's not very efficient. A real-world antenna, like the one on your router, is way more like a spotlight. It takes that same amount of energy and focuses it into a concentrated beam.
And this leads to a fascinating and kind of funny detail about most Wi-Fi routers. A standard antenna doesn't radiate in a perfect sphere. It radiates in a shape, like a donut. Seriously, this means if you are directly above or directly below the antenna, right in the donut hole, you're in a total dead zone. And yeah, that's why just tilting the antennas on your router can sometimes make a huge difference.
So with signals bouncing, bending, and shattering all over the place, how on earth can engineers possibly design a reliable network? I mean, they can't map every single object in a city, so instead they use some really clever mathematical models to try and predict all this chaos.
One of their most important tools is something called the path loss exponent, which they usually just call n. Remember how in that perfect empty space, the signal power dropped by the distance squared? Well, n is the number that adjusts that formula for the real messy world. A bigger n means a tougher environment, and it means the signal is going to fade way, way faster.
And just look at how dramatically the environment changes things. In that perfect free space, n is 2. But move into a city and it jumps up to around 3.5. Now go inside a building with lots of walls and floors, that n can be as high as 6. This means the signal weakens exponentially faster just by being indoors. The environment, it turns out, is everything.
But even that isn't the whole story, because n only predicts the average signal loss. The real world has big random obstacles, right? Like a concrete pillar in a building, or a bus driving by on the street. This effect is called shadowing, and it adds this layer of total randomness on top of everything else. It's the chaos factor in wireless communication.
So, if we only cared about that average path loss, a map of a cell tower signal would look like a set of perfect circles. Super neat, totally predictable, and not at all what it's like in reality.
Because the moment you add in the random effect of shadowing, that perfect circle gets warped into this messy, irregular kind of amoeba-like shape. And that is why you can lose your signal just by taking a few steps to the side. You haven't moved farther away, you've just walked into a signal shadow.
This whole thing seems almost impossible to predict accurately, doesn't it? But engineers now have a seriously powerful new tool in their arsenal to model this messy reality and build way smarter networks. For decades, planning a wireless network involved a lot of, let's be honest, educated guesswork with these statistical models. But today, that's getting a massive upgrade. Engineers can now feed huge amounts of real-world signal data, from our own phones, into AI systems. These systems learn the unique signal fingerprint of a city or even a specific building, creating prediction models that are more accurate than anything we've ever had.
So why does all this matter to you? Well, it's simple. A more accurate map of this invisible wireless world means engineers can place cell towers and Wi-Fi access points much more intelligently. And that means fewer dead zones, fewer dropped calls, and ultimately, faster, more reliable connections for all of us.
So, the next time your video call freezes or your song stops streaming, just take a look around. You're not just sitting in a room, you're in the middle of an invisible obstacle course. And now you know its journey is a constant battle against distance, reflection, and shadows. The only question is, what's getting in its way right now?